us to build amazing technologies and really, really smart telescopes. So this talk is a general talk. I'm assuming not everybody is a high crack radio astronomer. So I might say some things and you'll think, yes, I know that, so that's good. I'd like to give you an overview. So today's astronomy is the history of the universe. The history of the universe and its fundamental physics. Actually, what's in the universe? It's much why, but what we're dealing with. Everything from testing general relativity, the very first stars and galaxies. How and where did they form? What did they look like? How do we detect these things? Galaxy evolution, how did the galaxies then evolve? What shape is it in? Cosmology is about how do things clump together. The cradle of life. So we're here, we're life. Where is other life in the universe? Cosmic magnetism, because we know magnetism is a fundamental force and a feature that truly holds galaxies together. And the big one here, which is all about exploring making discoveries, is finding things we did not expect, exploring the unknown, building smart telescopes and instruments that discover things we didn't even know we were looking for. So that's pretty much what we work to. We don't do quite all of this, fair enough. I've had the opportunity to see this beautiful facility. Well, this is Astron. This is our building. We are in a woodland area, very flat. Well, the Netherlands is flat, but we're in a big woodland area in the Netherlands, in the north. We have about 250 staff in this building. This is just Astron plus JIVE, a smaller institute. And this is the Dwingler telescope. It looks much bigger in this picture. It's 25 meters. This was the first telescope built by the Netherlands, in the Netherlands. It was built in 1956. And as I mentioned to a few people this morning, when it was built, it was the world's biggest telescope for a few months. And it was totally eclipsed by the Lovell telescope, which was built very soon after. But that's history, okay? So when it was built, it was state of the art. And today, it has been, you might think it looks good for its age. It does, because it's 70 years old. It has been refurbished, and it is used by our local amateur society. So it's used as a hobby telescope and also for training, for outreach, but not very much. But at least it moves, and my office is on the corner, so I have a beautiful view on campus. Anyway, so this is Astron. We are in one place. We are a government agency, pretty much similar to NARIT, and we have very close interactions with the 4 universities in the Netherlands who do astronomy research, and then also the 6 other universities that do radio physics engineering and electronics engineering. So we have very close relationships with them. Now, the Dwingler telescope was built to do, someone asked me this question, actually it's a good question. So astronomy in the Netherlands was driven by astronomers. You might think that's an obvious statement, but it's not obvious. In fact, it really was driven by astronomy. Oort, you can't hear me. Okay, oh sorry. Oort realized, Professor Oort realized we ought to be able to see H1, neutral H1 in our galaxy. This was the 1950s, and that's why Dwingler was built, to do L-band H1 astronomy, and made the first map of the neutral hydrogen in the Milky Way. That actually set the scene for Astron's strengths in H1 astronomy. That became very much the strength of the Netherlands in radio astronomy. So, next couple of slides may be a little dull, but I'm hoping at least you get some sense of how we organize and how big we are. So, in Astron, and we flip to Dutch in places, in the organization, we have 3 major groups in the building. We are 180 staff, plus a lot of PhD students. We have an astronomy group. At the moment, the interim head is Jason Hessels. You might know Jason, he's a Pulsar astronomer. About 25 staff. That's all the astronomers who spend their time doing full-time astronomy. There are lots of other people in these other groups who have a PhD in astronomy or engineering. In Radio Observatory, we have 65 staff, or thereabouts, who run LOFAR, run Westerbork. So operations, running these major facilities. And our research and development group is the biggest. There's about 85 engineers. This is research technology research. This is not putting things on telescopes tomorrow. It's thinking about what will our telescopes do in 5 years or in 10 years or even in 20 years. It's the real strength of Astron. And then we have a lot of support staff. We do run everything else you do. And here's our family photograph. And we're multinational. That's pretty obvious, I guess, from the picture too. Lots of Dutch, but then lots of other nationalities on staff. So this slide I put in just to really point out that whilst our strength is in the basic research, it's our astronomy group here who really interface to the whole of the Netherlands researchers and to the global community. So globally, we know astronomy, we want to use the best instruments. We want our instruments to be some of the world's best. How do we do all of this? And there's an awful lot going on, as we know. So back to the picture, it's much more fun. So today, if you came to Astron, I would show you 3 key things that we are working on and operating now. There's plenty of technology development I'd show you too, but these are the big telescopes. The Westerbork Synthesis Array, which is 20 kilometers from our headquarters, consists of 14 dishes on an east-west array. Each dish is 25 meters in diameter, and it's currently equipped, or just been equipped, with the apparative phased array feed on 12 of those dishes. So this is the revolutionary multi-pixel, it's a bad word, but a multi-element phased arrays feed system on a dish, which increases the field of view by a factor of 40 on each dish. So it's a wide field survey telescope, basically. Very somewhat similar to ASCAP, if you know anything about ASCAP in Australia. LOFAR is the low frequency array, which is very unphotogenic. Dishes are beautiful and LOFAR is dipoles. LOFAR is a dual array running from 30 megahertz to 240 megahertz, but with 2 different antenna types. This is the central core. This is the heart of LOFAR. Again, this is quite near Dwinglo, it's at Exlo. And there are actually 6 stations on this island. It's literally a moated island in this wild space in the Netherlands. The LOFAR is made up of 51 stations, and we're the biggest owner share of LOFAR, very obviously. And the other big thing, of course, we've been working on for many years is the development and design of the square kilometer array. And we've been in what's called pre-construction with our partners, with the international partners, to come up with the design of this huge telescope to be split between South Africa and Australia. I'll show a map of LOFAR next, because LOFAR is something else. SKA low is one spec, but LOFAR, I said it's 51 stations. 38 of those stations are in the Netherlands. There's the Netherlands, lots and lots of dots. And we have stations that are linked, and this all works as one telescope, stretching from Ireland to Sweden to Poland, and in fact to Latvia. Sorry, Latvia, you're not on the map, but Latvia's there. Poland, 6 stations in Germany and France, and Britain. So LOFAR is a huge, those baselines are 1,300 kilometers, 1,300 kilometer baselines at tens of megahertz. Arc-second resolution, low frequency radio astronomy. It's completely groundbreaking. So, all right, you've seen that picture. So this is what, in fact, this is the Equivalence site. This is a LOFAR station in one of 6 in Germany. This is what a LOFAR station looks like. These are the very fairly dull and very simple looking low band antennas. And then this under the black plastic are these tiles of what we call the high band antennas, which if you've seen what we call bow tie antennas. That's exactly what they are. And these two sets of antennas will work in tandem in 2 years' time. At the moment, you can use one or the other. And as another picture of Westerbork, because we have just upgraded it with this apparative feed. There's Westerbork in the woods. And now on the sky, forming 40 beams simultaneously using this Vivaldi phased array. As I said, it's somewhat similar to ASCAP in the southern hemisphere. So there's a little bit of overlap between these two arrays on the sky, not a lot. This is at -30, this one's at +50. But we can get to some common reference fields, and we will be doing this. Okay, so what do we do with Apparative on Westerbork? Well, it's a survey instrument. That's a clue. It means we can cover the whole sky fairly quickly in a matter of a couple of years. And this, if you can see it, is a sky map of the tiles, basically working across the sky to survey H1 in galaxies, out to redshift about 0.3. Obviously, radio continuum studies, mostly H1 though, the H1 content of the universe. And at the same time, because it has such a large field of view, so 40 times the full moon, you can detect transients just because they're in the field of view when you happen to be looking in that direction. And we have a multi-year survey program defined, which is just getting going. We're right in science commissioning. Now these feeds, I don't know how much you know, but these types of feeds, this is what the front end looks like. It's basically a huge matrix of Vivaldi feeds. These feeds are very complex. They're very complex to calibrate and image. And we're very proud that we can actually make compound beam mosaics directly now through this system. This is a really big system upgrade to a 50-year telescope. And for someone like myself who really thrives, my science works from large surveys. I'm interested in the gross evolution of radio galaxies, so this to me is perfect. To most people it looks like a lot of dots, unfortunately. But this is perfect because it means we can really cover the sky, agile, and we can also do multi-epoch surveys. We can come back and survey the sky many, many times. So that's where Apparative is. It's our new system now on sky. LOFAR is doing wonderful things I'll come to later. And so the third prong in all of this is the SKA, and these are artists. Actually, this isn't an artist view, this is Meerkat, which of course is now built and will be extended to be square kilometre array mid-frequency. And this is the artist's impression of the low frequency SKA in Australia with these fairly tall, long periodic antennas. So those two instruments together form the square kilometre array, to go from tens of megahertz to tens of gigahertz. And then you might say, well, why build that as well as LOFAR? Well, the two things are very, very complementary. As I've said, LOFAR actually goes to lower frequencies than SKA low and has this incredible baseline distribution across Europe. But on the other hand, SKA low will be higher frequency. It will go up to 350 megahertz, which is beyond LOFAR's capabilities, particularly in the environment we work, and actually will be larger in terms of numbers of dipoles, and they will be closer together. And that's more optimized for certain types of science. So all of that's wonderful. So we have two large arrays. We're in the middle of Europe. We're doing great stuff. So fundamentally, this means Astron has to choose some scientific focus areas, our strengths. As a research organization, we could do everything, but we pick a few areas. And for fairly obvious historical reason, H1 in nearby galaxies is one of the strengths and has driven a lot of what Astron has achieved. Pulsars, transients, GRBs, they're all hot. FRBs, very much a strength of Astron, and our instruments are very well suited. EOR, the epoch of reionization, this era in which we hope to detect the H1 phase shift in the universe as the first stars and galaxies formed, LOFAR was designed to capture that signal, basically. It hasn't done it yet, but it's got 2,000 hours of data in store. We've captured that through LOFAR, and the teams are processing that data slowly. It is a massive, massive challenge to look for this incredibly tiny signal amongst the LOFAR data, because everything is a foreground to a very, very faint signal. So that LOFAR was optimized for this, and we still hope to get a signal. And then there's lots of work on AGN and clusters and galaxy radio galaxy studies. And the emerging one, which I did put on here because I think it's important for us all to know, is data science. That the increasing size archives and the massive amounts of data that we have. Our LOFAR archive at the moment is 31 petabytes. I told someone 30 this morning. It's 31 petabytes. If you are mining that, if you want to look for trends even in one area of sky, you need to be able to very confidently manage that data. So data science is an increasing skill for astronomy. So I thought I've got a couple of highlights of things that have come from Astron Science recently. Hopefully some of them will appeal. The first one is a pulsar that challenges most models of pulsars. I'm not a pulsar expert, but I understand that it's incredibly slow to understand how you can have a pulsar that really rotates this slowly and is so powerful. So this was discovered. You can see it. This is a LOFAR, low frequency survey. 150 megahertz, and you can literally see this all switching on and off, and it turns out it has a period of 23.5 seconds, which is kind of unique. The next one is another pulsar piece of science. This is just an accident, Michael. I didn't pick these particularly, which is using a pulsar triple system to test the equivalence of gravitational and inertial mass. Are they the same thing? We tend to assume that they are, but in this triple system and the way in which these sources interact and are literally falling towards each other and slowing because they're emitting these very standard clock signals, you can actually test the ratio of these two masses, and you find that it is less than 2 times 10 to the 6, sorry, 2 times 10 to the 6 in ratio. These things are, we're starting to understand these really are the same physical idea. And I've already mentioned lots, but this is the LOFAR 2-meter sky survey, which is underway. This is using LOFAR at 150 megahertz to basically, again, cover the entire northern sky, survey the entire radio universe at these frequencies. And yes, they're blobs. If you're into radio galaxies, I promise this is thrilling. If you're not, yeah, it's blobs. But this is the amazing zoom of radio galaxies and some other nearby phenomena, but in this case, galactic clusters, spewing out massive amounts of radio energetic energy over the entire epoch of the universe. This survey is so sensitive, it goes down to tens of microjoulskis, 30 microjoulskis. These frequencies, it's so sensitive, it basically picks up every single galaxy in the universe. You're basically looking line of sight to, we hope, the beginning of the galaxies. And that leads to this, the best limit, or the best detection, or non-detection, as it is at the moment, in the epoch of ionization that stands is from LOFAR. Other upper limits have been retracted from the press. This is completely unremarkable. Of course, you realize this is just noise. And this is what this subject is about still. It's about beating down the noise of the instrument and the complexity of the sky and trying to get the statistical signal from the data. This was derived, this upper limit was derived from, this paper is from 10 hours observations. There is a new limit about to come out from 30 hours, and it really is a better limit. But this signal is so small, it's 10 to the minus 5 below everything else on the sky. It's, if it's your thing, you know how hard this is. But we'll keep going because there is a huge amount of data now on the archive, and LOFAR, we think, should be able to get this get down to the limit of the statistical signal in the sky. This is not detecting or mapping the signal. The EOR is just getting that overall pattern, if you like, on the sky. So that's a bit about science, but I stressed that Astron's real strength is in our technologies research, and that's what I'll talk about now. So very much, you won't notice this if you walk around, but you could break our technologies into three main areas. Very much at the front end, what I would now call smart compact receivers. And Astron has very much invested into long wavelength, meter, up to L-band receivers in the past. And we continue because we think that this is a great future for what we can do in the Netherlands and also to contribute to the SKA. Lots of design in new novel antennas, optical fiber and photonic systems, integrated photonic systems to go straight to digital and to translate everything as a photonic signal through the radio telescope. It's going to take many years to get there, but we're very, very confident on that one. And then to move to aperture plane arrays. So dishes are lovely. Believe you me, I think radio telescope dishes are lovely. But if you extract the idea of a phased array feed, you can basically put them on the ground as all sky monitors and eventually drive them as sophisticated radio telescopes up to gigahertz frequencies. And that's what we call something like 3D mid. Computing. So ultimately, many of our telescopes are becoming much more computing driven. LOFAR is a perfect example. SKA mid similarly. We take a very simple front-end antenna. We take a simple front-end receiver, easy to maintain, cheap, agile. You can build hundreds of thousands of these things. Ultimately, you need this thing at the back end to process the signals, to have a smart astronomy machine. So we invest quite a lot across this spectrum of research, particularly accelerators. And then it's okay to have the hardware, it's okay to have the software, but you better have some good algorithms to deal with all of this information. So this is sorting out the noise from the signals and doing it really, really smart. And across all three of these areas, we are increasingly driven to show societal relevance. So it's one thing that people are very interested in astronomy, but it's quite another if we can show that these ideas or these smart imaging algorithms directly translate into MRI imaging, brain imaging, medical communication systems. So all of these three things, these areas in our technology groups, also have a somewhat outward-facing view. We do the work for radio astronomy for the future, but we do keep one eye on how else it could be used. I'll come back to that point in a moment. And all of this is, with university collaborators. We do not try to reinvent things. That's probably the other key thing. We want to be good for radio astronomy, so we want to be smart in systems, but we're not here to reinvent things that, I don't know, Google or Intel or Philips are currently inventing. That's not the point. I'll come back to that point. Right. Other things Astron does, we have quite a strong theme because of this society relevance for education and outreach. We're obviously all about STEM. STEM is science, technology, engineering, and maths. It's a big drive to make sure students feel that this is a good career path, because you can get great jobs everywhere in the world. We have open days, girls' days, school visits galore, and we run professional training courses at high-end RF engineering. So that's very much peer-to-peer. Obviously, we have students, and we have internships at the slightly lower level than PhDs. Our communications group are very active, so we need to be in the press as much as anybody. We need to tell people what we're doing, otherwise, we disappear. Probably one of the most novel things we've done in the last year is this, which I hope some of you might even come on, we've set up a new training course with Jive. They've got the Astron banner, but it's Astron and Jive, to come and join us for a few weeks and learn how to operate massive arrays for the future. So this covers all aspects of what do arrays look like, how do you run a massive array and extract science. So that's a structured training course, and that will be running again this year, which was last year's training course. Oh, I've got to download something. Right, I'm going to skip. Oh no, I won't skip that one. I won't skip that one, but if you notice the link, I'm sorry, I didn't download that. It's an advert, and I'll explain why. Radio Astronomy and Society. So just to pick up on that theme, because it is an important one, I think we're all extremely lucky. I hope most of us work in jobs that we love. We get paid to do astronomy. We get paid to build amazing instruments. I can see someone smiling, that's good. I think we're very, very privileged. But the question is, what do we give back? I'm very proud of this. This is a bit of history of Astron I did know, but I had to be reminded. This is a paper that was written by 3 engineers in Astron in 1977. And if you may realize what it's about, but it is the fundamental algorithm that is embedded in Wi-Fi 802.11. It is the manipulation of the Fourier transform to basically sharpen the signal. And that idea was taken by John O'Sullivan, who was the middle author there, when he went back to Australia. And that was then the story about how 802.11 was developed. And actually why CSIRO government now owns the patent to that Wi-Fi system. But anyway, but the 3 engineers were at Astron. And I used that as an inspiration. It was an outstanding event. If you think about how Wi-Fi has changed our world, fabulous. But when they wrote that paper, they weren't thinking of Wi-Fi. They were thinking of imaging black holes. And so it's a really important story that we do this amazing science, which was all very, distant and very abstract, but occasionally something comes out. And the link here is to the Skoda advert, the car advert, which is always worth watching because it features John O'Sullivan, being very modest. I just happen to invent Wi-Fi, which is lovely. Okay, all right, so how do we better that? I don't think we ever better inventing Wi-Fi as a community. But things like this, I think, are really important. This is just an image. But what this project is, apart from being called Disturb, which is a terrible acronym for a project, it's actually a project we've been given by the Joint Defence Force, but we're basically using a version of LOFAR. Now, LOFAR running from 30 megahertz, from 10 megahertz, sorry, to 3 gigahertz. So using our antenna technologies, it makes us extend our LOFAR knowledge up to 3 gigahertz with planar arrays and come up with a prototype system. It's basically solar ionospheric disturbance monitoring. So this, again, is something that we kind of spin out along the way. And talking of spinning out, where are we going? If I came back in 5, 6 years' time, what would Astron look like? Well, I think that this is what we will look like. There will be more. But I hope by then we will see the SKA being built. There will be some sort of science operations from these basic whatever's built in place by mid-next decade. We will have a science data center, which I didn't talk about, but algorithms and data science based on the LOFAR archive already are making us embed very much a center of excellence for Europe on astronomical data science. It's a very core skill at Astron already, and it's only one we are continuing to build. And we're using private providers. We're not just building a big data center. LOFAR will continue. We're in the middle now of upgrading, and we called it LOFAR 2.0. So Apple can do it, so can we. So this is LOFAR 2, like the iPhone 7. And it will only continue and grow. We already have more orders, so that's going to be doing even higher resolution, low frequency radio astronomy. And the other frontier, which I did mention to somebody this morning, is space. So this is not real. This is a conception of a CubeSat array, low frequency array in space one day. I think it's very possible. This is heading towards the dark side of the moon. This has got an ESA logo on it. Well, maybe, we'll see. But we're getting there, because already Astron has built and is now in space a low frequency 3-dipole radio telescope, which is already on the back of Chang'e 4, the relay satellite on the backside of the moon. So that's sitting there, it's just being switched on. I actually don't know if it's going to work, or we don't know if it's going to work. But it should do, because it embeds the LOFAR receiver system with a simple suite of antennas, and we will see. We will see. This is very much a prototype. But after we have exhausted all of the great sites in the world to do radio astronomy, if we want to continue and go below 30 megahertz, this is where we have to go. We have to go in space. So, where our sights are set. So, maybe a little like Merit, we are based in the north of the country. We're based in Drenthe, which is one of the provinces of the Netherlands. And it's an important point that we are in a province that is mainly agricultural, so we're a high-end, high-skilled workforce, and very inspirational for the students in the area. So we often put made in Drenthe, and everyone's happy about that. And then that's also the other killer, is that we're not just in the Netherlands, we work with everybody around the world. So, thank you very much. Questions?
Anybody has a question?
Yes.
Got one. This satellite that has recently been launched and is going to be switched on, where is the command and control for that satellite happening? Is Astron operating that?
No, it's in China, because it's on the back of the Chang'e 4 mission.
Oh, okay.
So it's in Shanghai.
So that's
Yeah. It's got a Chinese PI. And ESA and the Netherlands Space Office were asked to build a system to put on the back of it.
Oh, okay, so you're supposed to payload it.
Yes. Yeah. But it's a good, easy entry. I mean, obviously it took some years to get to the point of launch last year, but it's an easy entry, at least for us to see how robust our systems are in space. It's not our core business, or at least not yet. Everything we've built so far is usually at ground level.
Carol, I found that a very stimulating presentation. Is it too early for you to make some predictions about where NARIT can adopt some of the directions that you've gone down, particularly in terms of paying back society and involvement with defence and with other user groups, so that we can develop NARIT along those lines instead of just an optical and radio astronomy?
Okay, well, as you can see, Astron in the Netherlands has, or actually Astron chose the low frequency, long wavelength path. LOFAR has been around for about 10 years. I probably forgot to say that. It was actually built 10 years ago. It's taken many years to get to real, full science productivity. It's really now maturing. And one area I didn't talk about is us learning to really, as much as we run the training on running a big array, we're still learning too. Our systems are still shaking down. So it's a bit of an answer to your question, but one reason those European partners have bought stations, for some of them, they bought them standalone, because you can use a LOFAR station singly, very accessible. You may think they sound expensive, but you can buy a whole LOFAR station, use it separately. You won't be able to link to our system, it's a bit too far. Let's be beaten back by interplanetary scintillation, I think, but the idea that you can sort of add to your wavelength coverage, I think, is always very, very powerful. In the Netherlands, millimeter astronomy is not an option. Okay, we're at sea level, it's wet, it's cloudy, it rains a lot. We know our limits, so we've picked a spot that suits our climate and our skills. So I would suggest that the wavelength range is a powerful one. Something where you have a system that is accessible and you really can get data from it very, very quickly. The Irish LOFAR station does a lot of standalone work in this sphere. If you wanted a good model, they have a very active, school and graduate user base. And there are other LOFAR stations in the world that are not part of LOFAR International. They are standalone in other countries, and they're used for exactly this reason.
It looks like you are electronics. You have quite a number of engineers, research and development. So what kind of projects or systems that are being developed at the moment?
Right.
Just from the list, it seems like there's only Westerberg and SKA. LOFAR, but is that it, or there's more?
There's a lot more, because what I was trying to do was pick between, these are the system implementation, if you like. These are the things we build now and build in the next few years. And then that three-area research technology slide, there's many projects in there, but they are research projects. They don't leap. There's a gap, if you think about, not gap, there's a big leap between something that's a research project on the bench, a new photonic system, and then saying, let's implement it in here. There's a big step there, and it's really important to realize that difference. This is a huge upgrade program on LOFAR, but it doesn't include a lot of research. The research was done 6 years ago, or 3 years ago. We're now implementing the research we did for the past 15 years to upgrade LOFAR, but treat them very, very differently. It's really important that the research theme is research, and it's very blue. It can be very blue sky. We know what we're trying to do, sort of, but we're not going to leapfrog it from here's an interesting receiver to suddenly build a suite of receivers here. I take that difference very seriously. So these are the implementation projects that we're doing now. And then the other stuff, there's a whole series of about 30 research projects. And the research means technology, and research projects also means science. The astronomy research is also carefully scoped and bounded. To make sure we've got the money, by the way, as well. That's important, yeah. So, I can't see you speaking.
Me.
Oh, sorry, there you are.
So I just would like to go back to your organization structure again.
Oh, well, boring slide. All right, fair enough.
Because Saran is join us here now. I think he missed your very first slide, which is very interesting to see the number. Maybe where you show the number of the staff, that you have 15. About 25, right?
So 25 astronomers on staff, because our balance, there's 180 FTE, that means a few more people actually. Almost all of them are in these two areas. 65 in radio observatory, now that's running LOFAR. Now running LOFAR also means building smart, better observational systems. So 20 of those people do software all day, but we count them as radio observatory. And then this is our largest group, our research technology development group, about 85 engineers. So a huge strength of Astron. Yes.
How useful will be a station similar to LOFAR in Thailand, between Australia and Europe?
I don't know what your baseline to. You could baseline them to the NWA, I guess, but they won't be useful to Europe. The baseline's too long. I think there's a limit. We believe there's a limit due to the interplanetary scintillation. You'll be blinded, basically. So if you're going to have one, you must have a few stations. Buy 3. or have some neighbour countries buy some. Yeah, but Australia may be, but Europe's too far. There is a limit.
Carol, again, going back to
Yes, I can see you.
Going back to funding, you mentioned that, like NARIT, Astron is funded by government, but what percentage of funding comes in from industry and from partnerships with universities, given that you've got this enormous research and development group?
Yes, actually the R&D group are our biggest earners of external grants. They are actually. We spend almost all of our appropriation. So we have a base budget from the government of about 12 million euros a year. Almost all of it goes here. All right, so that's running, let's say, maintaining, upgrading LOFAR and Westerbork. These guys get a very small budget and then actually can earn, they triple what we give them in external grants and industry grants and whatever. And of course the astronomers are, I was going to say, fairly self-sufficient because they have research grants, but we do have quite a strong base budget for astronomy. But yeah, R&D are quite standout, high earners.
So is this a good model for NARIT?
Is it a good model? I'm going to argue it is, because I'm passionate about the technology research, actually. I think it's really important for any research institute to make sure our research is right at the cutting edge. And is, again, I will stress that we do not duplicate what other people are trying to do. So we try to be very aware of what NOAJ are doing or the VLA is doing. We are not out to replicate other people's research. We need to do something special, clever, and very much something that other people will want to. And I think having this model makes sure that our research engineers are sharp. They have to survive. They have to earn these grants. They have to be highly competitive to survive. To be honest, it's treating them much like research astronomers who live on soft money as well. Okay, so I think we do well because we invest most of our public money into being a really good observatory, being a really good provider of great data and observations, basically doing what we do really well with the telescopes that are currently on the ground, and then demanding these guys, and these guys, the researchers, are at the front end and are truly competitive on the world stage to make sure that they will be able to provide the instruments for the next 5, 10, 20 years. Yes.
Actually, I have a question. So we had this, at least to me, interesting point in the discussion in one of the Pulsar meeting. So, do you think the future of radio telescope would be large array or large dish? So, what do you think?
Okay, tough one. A large array, or you mean a large single dish? I'm afraid I'm an array person, so I've never done single dish astronomy. So I have a biased answer. I think there's room for both. I thought you were going to ask us another good question, but I think there's room for both. And let me answer why. Because the other question you could ask is, what's the future of radio astronomy? We're here talking about radio astronomy. Now, there's the whole optical, infrared, X-ray. Pick your favorite part of the electromagnetic spectrum. The world is amazing facilities being built and are in place. Now that's just the electromagnetic spectrum. We now have LIGO. We now have, we have gravitational wave instruments. We have KM3 nets. We have cosmic rays. We have different ways to detect the universe. And actually in the Netherlands, people talk about them as telescopes. Even LIGO, they talk about as a telescope. So what is the role of a niche, radio astronomer, and what does it mean, and what do our facilities mean? So I think your question is a good one. We have different ways of detecting the universe, but we're part of the big jigsaw to truly understand the physics of the universe. And we should think about our telescopes and facilities in that broader picture, and learning to use them together. I was talking with somebody about this. You've got a 2.4 meter optical telescope, and you will have a fantastic state-of-the-art 40-meter radio telescope. How are you going to use them together on sky? What science will you will have a pair of telescopes no one else has, as far as I know, not close together, working together in the same team, in the same building. What can you do that's truly different? Now we do something with LOFAR and Westerbork together now, we're just starting, but they're both radio telescopes, that's all right. But be smart, think about how you combine the facilities you have, and with others, it doesn't have to be national. But I think this is the future, to think about our telescopes and facilities and to think big, think above radio astronomy, think of them as just part of the jigsaw of what we're all trying to understand.
Any more questions? I think that was a great presentation, very informative. And Carol will be here with us today and tomorrow. She will join us for the